Okay, so what I'm going to do is I'm going to spend maybe 15 minutes or so just wrapping up some of the material in the first lecture. I know this is my third lecture, but it's okay, don't worry. So I'm going to spend about 15 minutes wrapping up the material in this lecture, and then I'm going to switch over to talking about Bayesian nonparametrics. Now, had I known that there was a chance UI wouldn't show up, then I would have prepared. He will show up. Okay, he will show up. We'll keep our fingers crossed. He's going to go into Bayesian nonparametrics a lot more, but I wanted to introduce some of the ideas a little bit because that gives me a good excuse to talk about some fun, interesting things we've been doing. Okay, so where were we? So we were talking about, just to backtrack, we were talking about the nasty computational problem that all Bayesians have to solve, which is doing integrals or high dimensional sums. And the good news is there are lots and lots of methods for trying to do these things. So I've reviewed Laplace, BIC, and variational approximations. Then what I'm going to do is very quickly, again, kind of one or two slides per topic, definitely very condensed way of presenting these things, cover EP, MCMC, and exact sampling. Okay, and then I want to get into a much more fun bit, which is kind of some discussion of pros and cons of Bayesian methods versus frequentist methods, and how we can all live happily together and not fight too much and things like that. Okay, so moving forward, that was BIC. This is variational lower bounds. Again, probably too hard to follow, but the best way to learn this stuff is actually to try it out on a small model yourself, to try to derive the equations yourself. And it ends up not being all that hard for models that are in the exponential family with conjugate priors and so on. Okay? And there are a lot of models that can be cast in this exponential family once you add in the hidden variables, and you could use conjugate priors, and then you can use this variational Bayesian EM algorithm, which makes it really nice. It's sort of a, in my mind at least, it's kind of a replacement for the EM algorithm. I really don't see much point running the EM algorithm. In almost all those cases, you can do the variational Bayesian version. Okay, unless you have something against doing Bayesian things. Okay, so we did the demo of the Gaussian mixture model. Okay, so this variational approaches are popular within machine learning. They were kind of developed, I would say, by having physicists sort of come into machine learning and teach other machine learning people some nice tricks, and then the machine learning people kind of developing those, and then coming up with very general methods for doing approximate inference in large complex models, and then doing it via message passing and graphs and so on. So it's been very exciting within machine learning. Interestingly, within statistics, it's taken them a lot longer to appreciate the usefulness of these variational methods. In statistics, oops, I'm jumping ahead of myself. People tend to focus on Markov chain Monte Carlo methods, MCMC methods for doing approximate inference in complicated Bayesian models. And I'll spend a few slides talking about MCMC methods as well. Before I move on to that, another class of approximations, which are kind of in this sort of family of deterministic approximations to these integrals, are given by expectation propagation, which I think Chris Bishop has talked about at a very high level, okay, without going into details. So I'm actually going to give you the equations, all right, on one slide. These are very general equations. You could actually go for a particular model and try to figure out exactly what these equations mean, but I also try to give you some of the intuitions about what's going on. So this is expectation propagation, or EP. And here's the idea. We're going to take, we have some data. Let's consider a simple setting where we have IID data, x1 through xn. So we have n data points. We have some model, p of x given theta. The model is parameterized by some parameters theta. And we have some prior on the parameters p of theta. Okay? So kind of a very simple, very general Bayesian inference problem. And now, what's our goal, generally, in Bayesian inference? Well, one of our goals is often to compute the posterior distribution over the parameters given the observed data, right? That's called learning. You had a prior, you observed the data, you compute the posterior, you've learned something about the parameters, you can then make predictions from that, okay? So, what does the posterior look like? Well, by essentially an application of the product rule. Actually, this is just Bayes' rule. The posterior is a normalized version of the prior times the likelihood. Okay? That's just Bayes' rule rewritten. Everybody happy with that? Good? Even if it's 9 in the morning? It's okay? Yeah. Bayes' rule. I've written it sneakily because I put the fraction here instead of at the bottom. Okay. It's still Bayes' rule. All right. So that's the posterior. And the way we're going to think about the posterior is simply as a product of factors. So for now, let's ignore the normalizing constant. Actually, EP will give us an estimate of the normalizing constant as a side effect anyway, so we're not really ignoring it. But just for the depiction here, I'm going to just forget about that for a second. The stuff in here, the stuff that depends on theta, is a product of n plus 1 terms. The first term, let's call it the 0th term, is the prior. And then the n remaining terms are the likelihood contributions from each data point. All right? So now we're not going to do anything fancy. We're just going to change notation. We're going to say this thing here, let's call it a product from I equals 0 to n of some functions fi of theta, where obviously f0 of theta is the prior, fi of theta for I not equal to 0 is each of these likelihood terms. Everybody happy? Again, I haven't done anything. I've written Bayes' rule, and I've rewritten it in some other notation. All right, now we're going to start doing something, okay? What we're going to start doing is, the general problem is that this posterior is a product of factors. Each factor might not be very complicated, but when you multiply n plus 1 of them together, you end up getting a really complicated thing, okay? This is generally the case. You can, just believe me, usually the prior, we start with a nice prior. If we incorporate one data point, maybe we can still compute the posterior analytically for one data point in a lot of Bayesian models. If we incorporate the second data point, then the posterior gets more complicated. And often, like, the posterior will have behavior that will be something like, okay, the number of modes in the posterior could, in the worst case, grow exponentially with n or something like that. That's why a lot of these posteriors are intractable to compute with, okay? So we're multiplying a whole bunch of factors together. That's our true posterior. And our goal in EP is going to be to approximate this by a product of simpler terms. Okay, so this thing in magenta is going to be our approximating distribution, which we're going to call Q of theta. It's going to be an approximation to our posterior. And it's just simply going to be defined as a product of terms, fi tilde of theta, where each of these terms is somehow simpler. So what do I mean by a product of simple terms? Well, if the fi tildes are in the exponential family, for example, when you multiply a bunch of things in the exponential family, you get another thing in the exponential family. I'll give you a concrete example. If fi of tilde was Gaussian in theta, when I multiply a bunch of Gaussians in theta, I get a Gaussian in theta, okay? Everybody happy with that? It's, e to the quadratic in theta. I'm multiplying them all up, which means I'm adding up a bunch of quadratics in theta. That's still a quadratic in theta. Therefore, that's still a Gaussian, all right? That sort of concept holds in general for the exponential family. So often in EP, what we're doing is we're modeling each of these terms as members of the exponential family. All right? So here's our goal. We want to approximate this hard thing with this easy thing. All right? So here is the ideal thing we'd like to do. Ideally, we would like to minimize the KL divergence between that hard thing and the easy thing, okay? If we were to do that, then, for example, we would be able to get the exact moments of the hard thing. So we would be able to get, if the easy thing, if Q was a Gaussian and we were to manage to minimize that KL divergence, then our approximating Gaussian would have exactly the mean and the variance of our intractable distribution here, all right? Unfortunately, that sounds too good to be true, and it is too good to be true. We are not going to be able to generally do that, all right? So this thing, globally approximating the intractable thing by this tractable thing, minimizing a KL divergence, is intractable. Here's a simpler thing that we could do. We could say, all right, we have n plus 1 terms here. We have n plus 1 terms here. Each of these terms is going to be something ugly. Like, each of these terms is going to be something ugly. Let's say this is fi of theta. We can approximate each of them by a simple thing. Okay, let's say that was f tilde I of theta. Okay, we could do that independently for each term. All right, that's the second option here. That's generally going to be very simple to do. We're just having to minimize n plus 1 KL divergences separately. I won't go into the details of how to do that, but for exponential families, that involves computing some moments of each of these distributions. And one at a time, these are usually easy to handle. Unfortunately, what happens there is, although it's simple and is non-iterative, you just do it once for each of the n plus 1 terms and you're done, it's going to be very inaccurate. And the reason it's going to be very inaccurate is that each time you're doing this minimization, you're introducing an approximation error, right? And then what do? You take a whole bunch of things, each of which has approximation error, and you multiply them all together to get something that has kind of the accumulation of all of the errors of each of the terms, okay? So that's also not good. Easy, but not good. And EP is kind of a compromise between these two. So here is, in one line, what EP is going to be an iterative algorithm, but each step of the algorithm is going to minimize a term that looks like this. So what does this look like? Well, this says I want to approximate fi of theta with this f tilde I of theta. So I minimize this KL with respect to f tilde I of theta. But I'm not going to do it in isolation like I did here. I'm going to do that approximation in the context of all of the other f tilde j's not equal to I. Okay? So I multiply both sides of this expression by all the other fj's. And then I say, having sort of accounted for the effect of all the other fj's, what's the best way for me to approximate fi with f tilde I. All right? And it's a very clever thing to do because essentially the product of all the other fj's is just simply going to be a simple distribution, for example, a Gaussian. Okay? So this just says multiply this nasty bump by some Gaussian that's going to tilt it in some direction. That's accounting for all of the other approximations that we've made so far. And then this f tilde I is also going to be multiplied by that same Gaussian. You're trying to match these two distributions as well as possible. Okay? So it's not completely global, but it's not completely local. It's somewhere in between. And it ends up being iterative because these guys, the f tilde I is going to depend on the f tilde j, so you have to keep sweeping through the index I to do this. But it's going to be a hell of a lot more accurate than this method. Okay? I won't go into the history. EP had, precedents. There's something called assumed density filtering, which was very well known. It was a single pass algorithm. And EP, all it did was notice that you can generalize that to go not just forward, but forward and backwards, and generally in other graphical model structures turn it into a message passing method. So here is the algorithm essentially in one slide. I'm going to actually skip over this because I think I've tried to give you the main intuition. The algorithm is basically for each of these terms I, you remove it, you minimize the KL divergence, and then you add it back in, and then you keep going back. Yep.
Is there any reason why this KL divergence was chosen to be minimized? Because in VV, you minimize the opposite KL.
Yes, excellent question. This KL divergence is the KL divergence between the exact distribution and the approximating distribution, just to clarify your question. In variational base, we were minimizing, I'll just remind you, we were minimizing the KL divergence between the approximating distribution and the exact distribution, which is the other way around. Now, the beauty of variational base was that we could exactly compute that lower bound, whereas EP doesn't give you anything like a lower bound. But in a sense, the KL divergence of the using the exact distribution on the outside is more the KL divergence that you'd ideally like to use. Because if you were able to do this intractable thing, which EP doesn't, by the way, to be clear, it doesn't do that, right? But in the dreamland, we have a dream, right? And our dream is to minimize this KL divergence. And basically, in that dream, if we were managing to do that, we would get the exact moments of the true distribution. So this is really a better KL divergence to minimize. Any other questions about this? Okay. Yes? So it's, I can't show it on this slide, but basically what's happening is every time you're doing one of the steps of EP, you're computing a term where if you combine all of those terms, it gives you an estimate of the normalizing constant. So you're locally computing part of the normalizing constant for each step of the EP algorithm. But I can't really go into it now because I think, first of all, I would have to rederive it because I didn't show it at all on the slides, and I would probably get it wrong. And that would waste your time, and then you would get angry at me, and all terrible things would happen. Okay. All right. Okay, it's a very nice algorithm, message passing in a graph. Like belief propagation message passing can be thought of as a form of EP. It's very general and nice. All right. So as I said a couple minutes ago, in the statistics community, for decades, since statisticians got computers, basically, they have been using MCMC methods to do inference. So just a very, very quick overview of sampling methods. So here's the basic idea of a Markov chain Monte Carlo method. About half of you say that you already know about MCMC. Is that right? It's not a question that any of you can answer, right? Individually, right? Okay. So assume we're interested in drawing samples from some desired distribution, P star of theta. For example, P star of theta might be our posterior, P of theta, given the data for some model, M. Okay? So what we're going to do is we're going to create a Markov chain, so samples theta 0, theta 1, theta 2, theta 3, etc. It's a Markov chain because each sample only depends on the previous sample. Okay? And we're going to create it in such a way that theta 0 was drawn from some P0, theta 1 was drawn from some P1, etc., with the property that Pt of theta prime is Pt minus 1 of theta passed through some transition function. So the way we're going to draw this Markov chain is really we're going to draw theta 0 from P0, and then we're going to apply some sort of transition operator that produces a jump from theta 0 to some theta 1. Okay? And implicitly, theta 1 has some distribution P1 now. Then we apply this random transition operator. What I mean by that is some sort of operation that reads in random numbers and makes a change to theta. Okay? And then we go from theta 1 to theta 2, etc. So we have a chain of thetas. This T is the Markov chain transition probability. P star of theta is invariant or stationary distribution of the Markov chain defined by T. If it's the case that P star of theta, when you apply that transition operator, what you get back is P star of theta. Okay? In other words, that transition operator doesn't change P star. Okay? It's like a fixed point of this system. All right? So our goal in MCMC is we can't generally, and this, just believe me now, if you don't know this already, in general it might be extremely hard to draw samples exactly from the posterior, let's say, but it might be actually quite easy to define a transition operator such that if you start anywhere, when you apply that transition operator enough, what you get is samples from the posterior. Okay? So defining these transition operators is generally going to be much easier than drawing from these posteriors directly. Okay. And there are a few recipes for defining these transition operators. These recipes are called things like Metropolis Hastings or Gibbs sampling or hybrid Monte Carlo or whatever. Okay? All right. So here's just a recap of what I said in the last slide. One useful condition that implies invariance is this thing called detailed balance. It's a bit stronger than just the invariance. It says if I started from P star and I applied the transition operator, then the probability of that is matched by starting from P star at theta and applying the transition operator in the inverse direction. Okay? So it's detailed balance. Okay, here's a good analogy for thinking about detailed balance. You know, in the European Union, every once in a while, borders get opened up for people to go from one country to another. Then the local press, at least in Britain, will get really scared and say, oh my God, we're going to be invaded by all these people from country X or whatever. Okay? That's because they feel like they're not in detailed balance with the population of country X. At some point, lots of people from country X come to Britain, they get some jobs, they decide they don't like the weather, and they start going back. Then you get detailed balance. Okay, then basically, you have a population of a country X, which might be small, then you have a population of Britain, which might be large, then the number of people going in this direction and the number of people going in that direction matches up so that the number of people is in equilibrium in some way. That's one way of thinking about detailed balance. Okay. All right. So MC and C methods define ergodic Markov chains, blah, blah, blah. Okay, so what we're really trying to get is we're trying to get so that this sequence ends up with samples from our distribution of interest, P star of theta. Okay, so that's basically a review of MCMC. Should I do a demo? Yes, I heard one person. That person was falling asleep, and she just heard the word demo, and she said yes. Okay. I'm going to do a demo of something called Gibbs sampling. Okay. All right. So this is the distribution we're trying to draw samples from. Okay. It's a top-down view of a bivariate Gaussian with high correlation. All right. Usually, okay, our distribution is not going to be that easy. If really we were trying to sample from this, we wouldn't be bothering with MCMC. Okay, this is a toy example, so you could see this thing in action. Gibbs sampling, what it does is it starts from somewhere. I purposely made it start from a really bad place. And then it draws one of the variables conditioned on the other ones, and then it draws the other variable and alternates in the other direction. It's a little bit like coordinate ascent, except it's not always ascending, right? It's sampling one variable conditioned on the other one, x1 conditioned on x2, then x2 conditioned on x1, etc. In general, in high dimensions, if you have a high dimensional distribution, it's very hard to draw a sample exactly from that distribution, but it might be very easy to compute the probability of one of the variables given all the other variables. So that's a situation where the high dimensional distribution is difficult to sample from, but the transition operator is easy to compute. Okay? So this time it's behaved extremely well. You see that it's sampled for a little while, and the samples seem to be covering the Gaussian reasonably well. Okay? That's Gibbs sampling. Sorry? Sorry. Okay, what's going on here? Yeah, what the hell are you doing? You're going to move on to the next demo without explaining this one? Is that the question? Something like that, yeah. Yeah. Okay, yeah. Yeah, okay. So, this Gaussian is meant to be the green thing is P star of theta. Okay? So I called it X, but I should have called it theta. Theta is two-dimensional, theta 1 and theta 2. What Gibbs sampling is doing is its transition operator that goes from a theta to another theta, right? Its transition operator is the combination of two transition steps, one of which samples, let's see if I get this right, theta prime, let's say theta prime 2 given theta 1, okay? So I sample 2 given 1, and then I sample one given 2. Okay? So I sampled the second dimension, the vertical dimension, given the value of the horizontal one. So I get theta prime here, and now at that location of the vertical direction, I fix that and I sample the horizontal direction given that vertical direction. So that's the transition operator for Gibbs sampling. It's a combination of two one-dimensional operations. In an n-dimensional Gaussian, this would be, the transition operator would be a combination of n one-dimensional operations. Okay. Is that clear? Yep. Excellent question, excellent question. You can randomize the order. Usually people sweep through the variables in some fixed order. You can randomize the order. You could do anything you want with the order. You can even visit some variables more often than others. So you can skip some of the variables. It's a little trickier to prove things for that, but it's still valid as long as you visit every variable infinitely often. Okay. And as long as the way in which you reorder the variables doesn't depend on the state. You can't say, oh, in this half of the space, I'm going to use this order, and in that half, I'm going to use that order. That could cause you problems. Okay. Any other questions? Yep. Very good question. No, you don't end up with an expression for the distribution. What you end up with is a bunch of samples. So what do you do with a bunch of samples? You can think of that as a representation of the distribution. You could think of that as a representation that looks like this. It says P star of theta is going to be approximated by 1 over L. Let's say I have L samples of so you're approximating P star of theta by a bunch of delta functions at the samples. You would usually throw away the first few samples because you start in a bad place and your guarantees are only about the equilibrium distribution of this MCMC. Yep. Okay. Here is just here's another demo. It's hiding behind that window. Okay, here's another. It's another distribution we're going to sample from. This time we're going to sample using an algorithm called the Metropolis-Hastings algorithm. Here we go. It's going a little more quickly. The Metropolis-Hastings algorithm proposes from, let's say, a ball around the current position, and it accepts some proposals and it rejects other proposals. So what I've shown you is the acceptances in blue and the rejections in red, okay? So you're supposed to ignore the red points, like don't even look at the red points. And what do you see here? So this distribution has 2 bumps. What do you see? It's not looking too good, is it? It never even, it's sort of like this species is wandering around and never even discovers that there's another island over there, okay? And what you really want is you want coverage of the whole distribution. So this is meant to show you that actually a lot of these sampling methods, in fact, a lot of approximate inference methods, when they fail, it's because there is multimodality in the posterior. Like they're exploring one part of the posterior and they're exploring this little hill here, but there's a mountain over there that they didn't even notice, okay? So that's an interesting failure mode to think about. But there's no magic bullet that's going to solve that in general. Because, these problems are computationally hard in the sense of like, hardness of computer science hardness, right? Okay, so that's kind of a tutorial of MCMC. I'm going to skip over this thing, which is a beautiful, beautiful idea that's hardly ever used in machine learning. This is called exact sampling, also called perfect simulation or coupling from the past. It's a way of drawing an exact sample from a distribution instead of starting at some point and going forwards by considering what would have happened if I started at every state infinitely far in the past with a fixed random seed, And then sometimes you can prove that a sample that you have is an exact sample from your true distribution. This is not strictly speaking an MCMC method, but when you can do this, it's a very, very interesting method to use. Hardly ever used in machine learning. And okay, so let me spend a few minutes discussion, and then I'm going to, this was much slower than I thought, but it's always worth it. Then I'll move on to Bayesian nonparametrics and some research things. So here's some discussion points. Okay, this is what I call myths and misconceptions about Bayesian methods. Okay, so here's something you sometimes hear: Bayesian methods make assumptions where other methods don't. Okay, that's completely rubbish, right? All methods make assumptions. If you don't make assumptions, there's no way you can say anything except, well, that was my training data. Okay? You can't make any predictions if you don't make any assumptions. All right? Don't be fooled by anybody who tells you otherwise. So otherwise, it's impossible to predict. So Bayesian methods, what they do is they put a straitjacket on you and they say, anytime you make an assumption, you have to write it down using probability theory. Okay? Okay, here's another thing I've heard. If you don't have the right prior, you won't do well. Well, in a sense, if you have a very poor model, you'll predict poorly, all right? But there's no such thing as the right prior, all right? Don't be scared, because it's not like you have to have the right prior. Your model, all parts of your model, there's no real distinction between the prior and the likelihood. They're all parts of your model. Your model has to be somewhat sensible, right? So it should capture a reasonable range of possibilities. So the way you could screw up is if your prior doesn't capture a reasonable range of possibilities. If it just puts all its mass on unreasonable things, then you shouldn't be surprised if you get unreasonable answers out of your method. Okay? Here's something a lot of people think. Well, Bayes is just like, you add a prior and then you do map. Okay? To me, that's really not Bayes. Okay, I'd rather just give that to some other community. They can have it. Map. I'll just say that's just very similar to regularization. It's not exactly the same as regularization, but it's very similar to regularization. It offers no particular Bayesian advantages other than you've thrown in a prior. The advantage of Bayesian methods is not that you're just throwing in a prior and then doing regularization. You might as well do regularization if you're going to do that. The advantage is it should really come from averaging over your uncertainty whenever you don't know. Bayesians tend to be very careful people, okay? We tend to worry a lot, right? We're like, well, we don't know, we better average over that uncertainty. I have difficulties making decisions because I always think, as a Bayesian, the optimal thing to do is wait as long as possible before you have to make a decision. So you collect a lot of evidence, okay? It's very difficult to plan a vacation that way. But, basically, this is the sort of part of being a Bayesian. You kind of average over uncertainty. You're always uncertain. You always think, okay, we need to wait to gather more evidence, etc. All right. Bayesian methods don't have theoretical guarantees. That's something else I've heard. Most Bayesian papers won't have lots of proofs in them. Okay, because most of the time you don't really need to prove anything. What are you going to prove? The sum rule and the product rule? No, you don't have to prove those things, right? So a lot of Bayesian methods, Bayesian papers, when you read them, they just feel a little bit like, okay, we use this prior and then we use this inference method and here are our results. And a reviewer comes back and say, where's the theorem? I'm missing something. I don't see the theoretical guarantee. It's often the case that actually, if a Bayesian were to be bothered about it, one could prove a frequentist theoretical guarantee on a Bayesian procedure. There's a huge community of people doing that. You can apply frequentist style generalization error bounds to Bayesian methods. And a great method for doing that is something called pack-Bayes. And a lot of the statistics community is interested in things like rates, convergence rates for Bayesian procedures, and so on and so forth. Okay, consistency, etc. So you can have theoretical guarantees. Most Bayesians aren't really bothered by that. Okay, but yeah, it's just a matter of taste. Okay, Bayesian methods are generative, so there's this distinction between generative and discriminative models. It's true that a lot of Bayesian stuff ends up using generative models, but you can have discriminative Bayesian methods as well. And when you learn about Gaussian processes, for example, you'll see a lot of stuff with discriminative Bayesian methods. So there's no one-to-one correspondence between those. Bayesian methods don't scale well. Again, it's true that integration tends to be more expensive than optimization. Okay, so there is some amount of truth behind every myth. There is some truth, right? Okay, so but we have a lot of inference methods, variational methods, MCMC, and so on, and it's possible to scale into very large data sets. In fact, some of the best performing industrial applications of machine learning are actually Bayesian applications. Okay, so I'll just skip 2 slides to something that Chris Bishop talked about already. For example, Microsoft's TrueScale ranking system is running Bayesian inference on a planetary scale. Okay, every player of Xbox Live has some latent variables that are being, inferred in a Bayesian manner from their games. Okay, so it's certainly possible to scale these things up. Okay, here's another argument. Surely Bayesian methods are not needed for big data. The argument goes like this: as the number of data points goes to infinity, Bayes approaches maximum likelihood. The prior washes out. Integration becomes unnecessary. That bit of argument is not incorrect. Okay, that's sort of true. But the problem with that argument is it assumes that we want to learn a fixed simple model for n going to infinity. And that's not really good use of big data, okay? So more realistically, I think big data is really often a large set of little data sets, like for example, in recommender systems or personalization or text documents, images, etc. There are, for any particular problem, there are only a small amount of instances. For any particular person, there might be a small amount of data about that person. There are millions and millions of people, but that doesn't make it a big IID learning problem, okay? And what we'd really like in those settings is for our models to grow, so the number of parameters should grow with the size of the data set. And that's what we'll talk about nonparametrics in a couple minutes. Okay. So reconciling Bayesian and frequentist methods. Frequentist theory tends to focus on sampling properties of estimators. Bayesian methods tend to focus on expected loss under the posterior. And there are some reasons why frequentist procedures are often useful to Bayesian. So for example, if a Bayesian A wants to convince Bayesians B, C, and D of the validity of some inference, where those other Bayesians might have different priors, then you need to basically show that your inferences are robust to the choice of prior, for example. And if you have a if you have a prior with good frequentist properties, then that will be essentially something that will be robust to different choices of your inferences will not be very different had you chosen another prior. Okay. So, okay, I'll just summarize. So probabilistic and Bayesian methods are simple. We just have 2 rules. They're general. We can apply them to almost any model. You avoid overfitting. It's not magic. It's just because you're not fitting. Okay, if you're not doing any fitting, you can't do any overfitting. All right, but you still can get bad predictions. All right, it's not that you can't get bad predictions. Just don't call it overfitting. If you're actually doing the integration, you're not really overfitting. They're a coherent way of representing uncertainty, and they guard against inconsistency in decision making. Okay, and I'll put these slides online. I'll send them to Philip, but there are a couple of review papers that sort of summarize at least my thinking on this stuff. There's one from 2004 called Unsupervised Learning that covers a lot of the material I've talked about. And there is a much more recent one that talks about Bayesian nonparametrics, which I'm going to have about 30 minutes to talk about. So I'll just skip to that. Okay. So of course, you can't make a whole research career out of applying the sub rule and the product rule to simple models. So what do we actually do for a living? I mean, what's the really interesting frontier of Bayesian machine learning? And I would argue that almost all the interesting stuff is currently centered around this area called Bayesian nonparametrics. The other bit that's interesting is just scaling things to very large problems. Okay? So both of those are interesting things to do. And of course, you could do a bit of both of them. Okay. All right. So we take the probabilistic modeling framework, but why Bayesian nonparametrics? This is what I mostly do my research on. Why? Everybody should ask yourselves, why are you doing the research you're doing? So there are two words here, Bayesian and nonparametrics. The Bayesian part, I think I've explained at length. It's basically the simplicity of the framework. Okay, it's very straightforward. The nonparametrics has to do with the complexity of any real-world data or phenomena we're trying to model. Okay, the framework could be simple. The laws of mathematics can be quite simple, but the real world doesn't have to be simple, right? So we shouldn't be applying simple models. That's the basic message here. So just to define a nonparametric model, and hopefully EY will have a lot more to say about this. A parametric model assumes some finite set of parameters. So given the parameters, future predictions are independent of the observed data, which we can write like this. The parameters are theta, as always. And therefore, theta captures everything there is to know about the data. In other words, if I know theta, I could drop the data when it comes to making predictions about future data x or any other unknown quantity x. Okay? So really, in a parametric model, these parameters are like a bottleneck. They encapsulate all knowledge about the trading data. And I like to think about these, in fact, I like to think about all modeling as some sort of information channel between past data and future predictions, okay? It's a communication channel in a sense, all right? And in a parametric model, the complexity of that channel is bounded by the finite set of parameters that you have, okay? So all information flows through those parameters into future predictions. That makes them not very flexible. Even if you have unlimited amounts of data, you're only going to have a finite amount of information passing through. In non-parametric models, we assume that the data distribution cannot be defined in terms of such a finite set of parameters. In general, in non-parametric models, we can often think of them as being defined using an infinite dimensional parameter space. So usually we think of this theta as some sort of unknown function, which is an infinite dimensional thing. Okay. And the nice thing about that is that the amount of information, this sort of, information highway from past data to future predictions is a lot wider because that theta has a lot of capacity in it. Okay? That makes them more flexible. So again, why do we work on nonparametrics? Because of the flexibility. What does flexibility mean? Flexibility means, we're going to get, we hope, generally better predictive performance. Our models are more realistic, so you can be a subjective Bayesian without feeling very uncomfortable. It's hard to be subjective Bayesian if you know your model is not realistic, okay? So, when you expand your space to be more realistic, it's easier to sort of feel comfortable with your assumptions. And then as a kind of lesson, I think almost all successful machine learning methods are either essentially non-parametric, where what I mean by essentially is that some of these methods, like for example, large neural networks, will have millions and millions of parameters. So they're really operating basically in the non-parametric. They're not limited by the number of parameters that they have. They're operating in this very flexible arena. Of course, successful methods are often also highly scalable, which is the other dimension of flexibility and scalability, basically. Okay, so if you get into this Bayesian nonparametrics field, what you find is a lot of jargon, like any field, but the jargon tends to be using terms from stochastic processes and probability theory. Did you have a question? Yeah. Uh-oh. I'm here still. Okay. Yeah?
This is only a problem if we have one set of parameters that we're dealing with. So you just told me that I should not do MAP, but I should actually average over all possible parameters. So it's indeed true that if I see more data, my posterior distribution over parameters changes, and so I can't just drop that data.
Okay. What this says is if you given the parameters, if you happen to observe the parameters, which you never do, then your past data would be independent of your future predictions. Okay? Your future predictions would be independent of your past data. Now, in Bayesian inference, you never observe the parameters, right? So you have a posterior over the parameters, but essentially the posterior over those parameters captures all the information about the past data. And as you get more and more data, that posterior is generally going to get more and more peaked around one value of the parameters. So essentially, eventually, you're given the parameters, even though you have infinitely many data points, you're stuck with one, Gaussian or whatever that you're fitting to the data. Okay, but it was a very good question, actually. Okay, so Bayesian nonparametrics involves a lot of jargon, things like you're going to hear about Dirichlet processes, Gaussian processes, beta processes, whatever. It gets a lot hairier than that, But the point is, like other machine learning people, we're trying to solve problems, okay? So the kinds of problems we're trying to solve are things that are very familiar, like function approximation, classification, clustering, time series, hidden feature discovery, etc. Okay? And in all of these cases, there are some very classical methods for doing that, like, polynomial regression or logistic regression and so on, mixture models and k-means. And a lot of these non-parametric models can be thought of as just extensions of these simple finite dimensional parametric models to the flexible infinite dimensional space. Okay? So this is kind of the mapping, very hand-wavy, just examples of things. Like, you could start with polynomial regression, and you could think about adding terms to it, putting some priors on it, and then in a particular choice of those operations, you end up with Gaussian processes as an infinite dimensional method, okay? Etc. And then each of these things is associated with a stochastic process, like a Gaussian process in these cases, which you'll hear more about, Dirichlet processes, Chinese restaurant processes, Indian buffet processes, etc. Okay? All right. So I'll try to explain a lot of these in the next few minutes. So here are the grandfather and grandmother of most non-parametric models. Okay, the Gaussian process and the Dirichlet process. The Gaussian process has been studied for over a century. The Dirichlet process since about the early 1970s, and they're basically not that difficult to understand if you already know the Gaussian distribution and the Dirichlet distribution. So the Gaussian process is an infinite dimensional generalization of the multivariate Gaussian distribution. It defines a distribution on functions. So we say f is drawn from a Gaussian process with mean, mu, and covariance function c. And here is just a sample of a single sample of a draw from a Gaussian process. Don't look for a Gaussian bump in this direction. Think of this as a function between x and y, and this is just a random function. And from one sample, you can't see what the distribution is, but if I showed you many more samples, you would get to see what a distribution over functions looks like. Okay? And the mean function is a generalization of the multivariate mean, and the covariance function is a generalization of the covariance matrix. The covariance function is also exactly the same object as the kernel in kernel methods like SVMs. Okay, it's a positive. It's supposed to be a positive definite kind of operator, basically. Now, a Dirichlet process defines a distribution on distributions. So if I draw from a Dirichlet process with some mean G0 and some concentration parameter alpha, what I get out is a distribution, which here I've represented as a little histogram. Okay? So it's a distribution over distributions. That's fine. A distribution is just a function that's non-negative and integrates to 1. So this is a general function on the reals. This is a function on the non-negatives that integrates to 1. Okay? And these are both random. Okay? Now, I won't say much more about Gaussian processes, but just to give you a bit of a teaser, I like to relate models with each other. And so if we start with a very simple model like linear regression, we can think of exploring other extensions of that model by applying different operations to it. So linear regression is a regression model. It goes from x's to y's, where the y's are real. We can turn that into classification very easily by just taking that y and mapping it through a squashing function and thinking of that as a probability of a label. Okay? So like the logistic squashing function, for example. If we do that, then we get from linear regression to logistic regression. So that's these purple arrows are turning regression models into classification models. Okay? Logistic regression, I hate the name. It should really be called logistic classification. It's a classification model. Okay? All right. Another operation we can do to any model is to models that are linear in the input, we can kernelize them. Okay, imagine I simply take the input, I map it into some feature space, and now I apply the linear method in that feature space. Okay, so you could do that to linear regression, you would get something that you could call kernel regression. Okay. A third operation, these blue arrows in this cube, that you can do is take a model and instead of doing point estimation of the parameters, do Bayesian inference over the parameters. That's pretty straightforward in general. So here we would get Bayesian linear regression, a very boring model that you'll find in every Bayesian textbook. Okay? Now, what happens if we apply these operations in various combinations? So, kernelized linear classification, okay, applying either the classification operation to kernel regression or the kernelization operation to this sort of linear classifier, ends you up with something like kernel classification. Roughly speaking, a support vector machine would lie here. Okay, it's a kernelized linear classifier. Okay, it's not exactly the kernelized version of logistic regression because the logistic function is a bit different from the hinge loss, but these are just examples of things that live in the corners of the cube. Okay, SVMs definitely live here. All right. Now, what about Gaussian process regression? So Gaussian process regression is when you use this Gaussian process, which has a kernel matrix in it, by the way, to learn regression functions from x to y. I'll talk about that a little bit, and Philip, I'm sure, will talk about it a lot more. Well, Gaussian process regression is simply Bayesian kernel regression, or alternatively kernelized Bayesian regression, right? And here on this corner we have Bayesian logistic regression, which is a very well-studied model. In fact, we were doing an exercise on Bayesian logistic regression yesterday, right? Or something like that. And in this corner here, we have kernelized Bayesian classification, which is Gaussian process classification, which you could think of as a Bayesian analog to support vector machines for classification. So all these things are related, and it's useful to know the relationships. Okay. All right. But that's, let me talk a little bit about the Dirichlet distribution. The Dirichlet distribution, because the Dirichlet process is sort of the grandmother, this might be the grandfather or whatever. So the Dirichlet process is an infinite dimensional generalization of the Dirichlet distribution. So let's talk about the Dirichlet distribution. Sorry, this slide is a bit heavy because it has a lot of kind of notation that you might want to use for reference. It's a distribution on the k-dimensional probability simplex. What that means is that it's a distribution on vectors, k-dimensional vectors that are non-negative and they sum to 1. And we write it like this. This is a distribution on these vectors with some parameters alpha. It's a Dirichlet distribution. There's a normalizing constant in green involving a bunch of gamma functions that I've defined at the bottom of the slide. And then it's a product of pj to the alpha j minus 1. The form of this is not all that important for our purposes today. Okay? Just think of it as distributions on vectors that sum to 1. All right? It has some nice properties. It's conjugate to the discrete or multinomial distribution. So that makes it very easy to work with. Okay? Because it's a distribution on the probability simplex, if I think about the 3 simplex, so theta 1, theta 2, theta 3, if they have to sum to 1, then I can just draw the distribution as a function of theta 1 and theta 2. And here I've drawn it as function of theta 1 and theta 2. It looks like a triangle because, remember, theta 1 plus theta 2 plus theta 3 have to sum to 1, so you can't have values on this side of the triangle. Okay? So the uniform distribution on vectors that sum to 1 is the Dirichlet 1, 1, 1 distribution. Okay? The parameter is 1, 1, 1. If I increase all the parameters, I get concentrated more and more around 1/3, 1/3, 1/3. If I vary the parameters, I can put more of my probability mass near the corners of the square, or even here near all the corners, but away from the middle of the triangle, not the square. Okay? So this is some intuition about the Dirichlet distribution. The Dirichlet process is an infinite dimensional generalization of the Dirichlet distribution on some space where if I were to take my space and divide it up into different chunks, let's say my space is the real line, if I were to divide it up into these 6 different chunks, then in the Dirichlet process, the amount of mass assigned to each of these chunks by a random draw from the Dirichlet process follows the Dirichlet distribution. And I think in the interest of time, I'm going to hope that Yiwai gets his visa. And I'm not going to cover this because I'm absolutely sure Yiwai will cover this material in his lecture on Bayesian nonparametrics. But I just wanted to give you a flavor of at least the terminology and prepare you, if you're not already familiar with this stuff, for things that Yiwai will probably talk about next week. Okay? Now, let's talk about some of these applications. So one of the applications of, one of the most widely used applications of Bayesian nonparametrics is clustering. And now what we're doing is not clustering with a finite mixture model, like a mixture of 6 components or something like that, but actually looking at clustering with infinitely many components. So why would you want to do that? Well, you might not believe that a finite number of mixture components can adequately capture your data. Like, for example, your data might have the distribution might have funny tails, or they might have structure at many resolutions, etc. In fact, for many kinds of data, you might naturally feel that the number of clusters might grow over time. So here's a very good example, which I think a lot of people find reasonably convincing. Okay, let's say you're employed by a company like, let's say, Google, to cluster news stories. Okay, so news stories are coming in all the time, and Google's goal is to organize all information or whatever, right? So you're trying to cluster news stories. How many clusters should you choose? What do you think? 5? There are 5 different kinds of news stories. There's whatever, celebrity news stories, war in some country that people in the West are not paying attention to. Okay, well, how many? Well, it's silly, right? There are many, many kinds of news stories. And as news, I mean, the word news is about new things, right? As new things happen, we might need new clusters, okay? So you're employed to do clustering. You feel uncomfortable about any finite number of clusters. You'd really like to have a model that, as it's doing clustering, a new news story comes in and it decides, that's weird. This doesn't belong with any of my previous clusters. I should create a new cluster for that, right? And that's a great application of Bayesian nonparametrics. This is probably one of the more successful applications of Bayesian nonparametrics. Clustering with infinitely many clusters. Or if you're uncomfortable with the word infinite, just think of it as an unbounded number of clusters. So at any point, the number of clusters is not bounded. You can always add a new cluster. Okay? So if you were to sample, this is a bit boring picture, it would be more interesting to show you news stories or something, but if you were to sample data from what's called the Dirichlet process, mixture of Gaussians, what you would get is, as you get more and more data, this is 10, another 80, and another 200 to get 300 data points. As you sample more and more data, you see more and more fine structure appearing in the data. Okay? And in fact, as you add more and more data, you will continue to grow in the number of clusters that you have. Okay? So how do people do this? Well, people define these, start with a finite mixture model. This is my favorite way of deriving Bayesian nonparametric models. Start with a finite model. Notice where it's finite, then take a limit. Say, all right, this is a mixture of k components. So what happens when k goes to infinity? Ooh, this sounds exciting. Okay, let's take k to infinity. All right. We've already seen the mixture model before, right? So you're all happy with that? Mixture of 6 Gaussians or whatever. So, okay, for k to go to infinity, we need to have these pi's, this vector of pi's, these mixing proportions, to be an infinitely long vector that sums to 1. Okay? Hint, that's where the Dirichlet process comes in. Okay? So if we start with a symmetric Dirichlet prior on the pi k, and then we take the limit as k goes to infinity, we rediscover the Dirichlet process that way. Okay? And Radford Neal, in fact, around 2000 or so, did that, and he kind of reinvented a lot of the stuff that people knew in statistics already. Okay? Yep, question. Yep. Yep. You could say, all right, here's a prior on the integers. Let's call it let's say a Poisson distribution. A Poisson distribution has infinite support, right? But the probability of k being large is very, very small. Okay, these two things sound very similar, right? They both seem unbounded, but in practice, they might even perform quite similarly. But philosophically, they're very different. Okay, I'll tell you philosophically what they mean. I'm working for, let's say, I'm not, unfortunately, I'm not getting that kind of salary, but imagine I was working for Google, and I was, clustering news stories. If I say there's a Poisson prior on the number of different types of news stories, and I just don't know what it is. Okay, it could be 7, could be 10, I don't know what it is. Versus the nonparametric thing, which essentially what it does is it puts all its mass on infinity. It says there actually are infinitely many different kinds of news stories, but I'm only observing finitely many of them. Okay, the difference comes in the limit. We never are in the limit, right? But in the limit, the Poisson model would actually infer some number of news stories. It would say, okay, there are 732 news stories. Okay, whereas the non-parametric model would keep adding new sort of topics as it goes along. Yeah. You have infinite amount of data, you have an infinite computer, etc. You know, that's all very nice. Yeah. This is why I'm not so into theory, right? But yeah. Yes.
But let's say you combine this approach with having a Poisson prior on K, you combine it now with model selection, like you did.
Yeah.
And then in principle it could be, I mean, then you average, you will integrate over K.
Yeah.
And it's, is it then quite similar?
It ends up being quite similar. Yeah, it ends up being, but it ends up being similar but philosophically different for the reasons I described. And it also ends up being sometimes algorithmically simpler just to take the infinite limit. It's actually easier to implement the infinite limit than the mixture of the finite models often. Not always. Yeah. Okay. Yep.
Hi. My question is, if I have a problem that has a finite number of clusters, and then I apply this technique, am I guaranteed that I find the right number?
Wonderful question. There is a very recent paper that shows no. That the answer is that there is a recent paper that shows that you're not consistent in discovering the number of clusters if you apply this method and there are actually a finite number of clusters. I could go into that. It's an interesting paper, but it doesn't surprise me because you've put all your probability mass on infinity. So if the truth is actually finite, then you're not consistent. You're going to overestimate. Yeah. Okay. I'm going to zip through a lot of the rest of the material because I'm told I only have half an hour. I'm told I have half an hour. No. Oh, one more question. Okay. Yep. From the observation room.
How can you be sure that each cluster corresponds to one new story and maybe one story maybe correspond to a mixture of two clusters?
You can't be sure. That's the short answer. Clustering is a very difficult to define problem. Okay, it's difficult to define when you have a good clustering. It's much easier to define when you have a good probability model because you can say what is the probability of held out data. So clustering, it's hard to make it objective. You could compare it to some ground truth if you had labels for what you want the clusters to be, but then it's almost like classification. All right, I'm going to zip through the rest. I'm told I have 5 minutes, and that's okay. Basically, in 5 minutes, there's no way in hell I could actually explain a lot of the research that we're doing, but what I'm going to do is give you a flavor for some of the stuff, and you'll see it zooming by. All right? And I will just freely skip over things. So here is some of the things that I find exciting these days. Bayesian nonparametric models for more complex data. So we already talked about clusters. We've done a lot of work on hierarchies, but I've grayed that out. I'm not going to talk about that. You can apply these Bayesian nonparametric models to time series. So I'll mention some of the stuff on hidden Markov models, sparse matrices and feature allocation models, and some network modeling. So here's time series, hidden Markov models. Chris Bishop described these. They have traditionally a finite number of states. Let's take the limit. Let's have hidden Markov models with infinitely many states. Okay, so that's called the infinite hidden Markov model. Something we worked on a little over 10 years ago. And essentially, the infinite hidden Markov model can be derived from within this Dirichlet process framework, okay, without going into details, it's nice because anytime you're using a hidden Markov model and you don't know what the number of states should be, you could instead use an infinite hidden Markov model, and it will allow you to have new hidden states appear over time. Blah, blah, blah. You can apply this to, doing kind of segmentation of time series or segmentation of videos, etc. Okay, sparse matrices and feature models. So clustering is all very nice, but in clustering, data points belong to one and only one cluster. Okay, but actually, in a lot of interesting scenarios, we would like to assign data points to multiple clusters simultaneously. You could think about it, or multiple hidden groups. So I'll mention in a few slides a very natural example of that. Imagine you're modeling a social network. A lot of people have done clustering of nodes in a social network, but I'm sure all of you would be offended if somebody said, you're a person that belongs in cluster type 37 of kinds of people or whatever. Because you say, well, no, I'm much more complicated than that. I have this bizarre hobby, and I went to this, exotic high school, and I have, my friendship network is actually captured by all of these different kinds of groups that I belong to simultaneously, right? So we want to move beyond clustering to a situation which we call feature allocation, where each data point can belong to multiple, instead of calling them clusters, let's call them features. Each data point can possess multiple features at the same time. So instead of this binary matrix, which has a 1 on each row, we have a more general binary matrix with multiple 1s on each row. This is the sort of classical stuff with the Chinese restaurant process and the Dirichlet process. This, which generalizes that, doesn't strictly generalize, but it basically extends that in a new direction. The analog of this is called the Indian buffet process. The analog of the Dirichlet process is the beta process in this model. Okay. Again, I unfortunately don't have enough time to talk about this. I think I probably will. So a lot of stuff has been developed around this idea of the Indian buffet process. And it can be applied to a lot of settings where clustering is just not appropriate. Like sparse latent factor models, models of overlapping clusters, where you can belong to multiple clusters at the same time. Models of graph structures, where a node can have multiple parents, right? You have to be able to choose which parents a node has to figure out what the graph structure is, etc. Okay, independent components analysis, versions of binary matrix factorization, etc. So here is again a picture, which if I had a lot more time, I could try to explain better. You could start with a finite mixture model, and then you can apply different operations to it. You could consider what is the time series generalization of a finite mixture model. So that's these orange arrows. That would be the hidden Markov model. What is the nonparametric version of a finite mixture model? Well, that's an infinite mixture model or a Dirichlet process mixture. Then these green arrows say instead of belonging to one cluster in a finite mixture model, you belong to, each data point belongs to one cluster. Extend that to be a feature model or factorial model, and that's these models here. So the IBP is kind of the factorial version of the Dirichlet process mixture, very loosely speaking. Then the infinite hidden Markov model is the time series version of the Dirichlet process mixture, or the infinite version of the hidden Markov model, etc. So there are various different models here. Okay, all right. So I'm down to 0, roughly. Okay. 2 minutes. Okay. In 2 minutes, I'll talk about 3 of our very recent research topics. Networks. We're interested in networks. Lots of people are interested in networks. We're jumping on the bandwagon. So networks are actually much more interesting than just networks, because you can think of a lot of relational data as a sort of network. So, if you have relational information, John is a friend of Mary, Jack bought an iPhone, Fred rated the movie Titanic with a 5, a lot of data in machine learning looks like that. That's what we're really interested in, is data that involves relations between objects and other objects with certain properties of those relations. Okay. So there are different models for networks. There are nonparametric models for networks, which do some sort of clustering of the nodes. There are models for networks based on the Indian buffet process, like this very nice model by Miller, Griffiths, and Jordan. Ooh, I showed that slide already. But we, in work with James Lloyd, what we've been interested in, it's a number of authors, which I show you on this slide. James Lloyd, Dan Roy, and Peter Orbance. We've been looking at kind of the fundamental statistical structure of relational data. So can we characterize in a very general way distributions over relational data sets? So there's a well-known theorem in Bayesian statistics called De Finetti's theorem that says any exchangeable data, exchangeable sequences, can be thought of as a mixture over IID data, a Bayesian mixture over IID data. And this motivates a lot of Bayesian nonparametrics. And what we've been looking at, and I really won't be able to cover this in 1 minute, unfortunately, what we've been looking at is this very interesting result in probability theory called the Aldous-Hoover theorem, which talks about exchangeable arrays. Okay, so instead of sequences of data, we're looking at arrays, which might represent networks. It might represent, users and ratings of movies. It could represent all sorts of array data that you would find in machine learning. And what this theorem says is that there is a very general way of representing all possible distributions over these arrays. And so we've come up with a model that uses Gaussian processes that ends up being a very general representation for multiple arrays of data. Sorry, again, this is just a vignette, basically. And a lot of existing models can be thought of as special cases of this kind of random function model. Okay. Another thing we're interested in is scalable approximate inference. So this is work with Colorado Reed, very recent as well, where essentially for the Indian buffet process, we really want to scale it up to work on very large data sets, and we're going to be a little trading off, we're going to be a little greedy here. We're going to use a maximization method as a way of doing approximate Bayesian inference. In fact, what we're using is something known as submodular maximization, which is sort of a diminishing returns property of certain maximization problems. And the really fun thing about doing this is that we can compare lots of different approximate inference methods. I've talked about some of these things like MCMC methods, variational methods, now this new submodular maximization method. The way I'd like to compare a lot of these methods is as speed accuracy trade-off. So these plots are interesting to look at. On this axis is time that a method is running, and on this axis is test set log likelihood. How good is it at predicting? And we'd really like to be kind of over here, methods that are very quick to run and that perform well. Different methods correspond to different trade-offs, and this is sort of applying these IBP type models to data sets that are larger than we've ever been able to apply before. So here's another. This is on a log scale now. Time and accuracy again, and different methods show different trade-offs. So it's just really useful to do that. The last thing I want to mention as a vignette is, again, kind of not possible to really explain this unless you've heard Philip's lectures on Gaussian processes. But one of the things we're interested in is structure discovery in these Gaussian process kernels. So Gaussian processes can be used for function approximation. Here is that diagram for Gaussian processes. Here's just a teaser. This is some other recent work that we've been doing on Gaussian processes for structured prediction. Okay, so again, structure prediction methods can also be tackled with Gaussian processes. And then we want to learn the kernel, lots of pretty pictures. So essentially, if we have data that looks like this, we'd like to extrapolate well. So if we really learn the structure of a time series, for example, these are the kinds of extrapolations that we get. And we'll get more interpretable representations of what these time series are. This is kind of all towards the ultimate goal of building an automated statistician, really, where you just give it some data and it tries to interpret it for you, and it gives you not a good predictive engine, but also getting scared here. A good predictive engine, I'm going to stand on this side, a good predictive engine, but that also gives you something interpretable to look at. All right, that's good, because I can finish now. So Bayesian machine learning is just simply the application of probability theory to learning from data. A lot of the work that we do is on nonparametrics because we want flexible models. And I gave you kind of 3 examples of very recent work that we've done in the last 5 minutes. Well, no, we did the work in the last couple of years, but I gave you the example in the last 5 minutes. And there are loads of people to thank for all that recent work. I have a bunch of postdocs, which I'm going to advertise soon on this mailing list, which you should all be signed up for because it's the main machine learning mailing list. Okay. All right, thank you.
Great. Thanks a lot. Okay, should we do one quick question?
You had a question before, so it's...
Yeah, well, I have a question about the parameters of finite distribution and inference process. I have seen people using finite distribution as base distribution for Dirichlet process, and I wondered why is that? Because I mean, probably
If you use a finite distribution,
you could probably represent this as a Dirichlet distribution.
yeah.
They kind of explain that it's because they are not able to come up with the non-symmetric parameters for Dirichlet distribution. Can you comment on that?
Yeah, I mean, if you, in a Dirichlet process, if you have a continuous base measure, you'll get, countably many atoms appearing. If you have a finite base measure, then you basically have a finite number of atoms, and so it's just a Dirichlet distribution.
Yeah.
So then I don't know, it's a Dirichlet distribution, but maybe they want to use some of the machinery or theory that's known for Dirichlet processes in that context.
The Dirichlet distribution that they would like to use has non-symmetric parameters.
Yeah. But that's fine. You can use Dirichlet distributions with non-symmetric parameters. I'm not sure I know what the, yeah.